Okay, so chapter 4 is finally getting into something that is really a different idea, and that is that instead of just describing motion, we were first describing one-dimensional motion, then two-dimensional motion, and really practice with that two-dimensional kinematics yesterday. We're now going to start talking about forces. We've been using an intuitive notion of forces, but a lot of times you'll find that your intuitive notions of forces aren't true, and some of you said so much in the reading responses. And the important thing that we're going to cover is Newton's laws of motion. You read about those yesterday. And they tell how an acceleration of an object is related to the sum of all the forces on it. So let's just sort of flip through at a high speed compared to what the video went through it at. A force is always an interaction between two objects. In other words, I might think I'm putting a force just down on this table, but I can feel that the table's pushing upward on me when that happens. When I pull on the door handle's pulling back on me. So it's impossible for one object to exert a force on the other without the other exerting a force on the one. And we'll see that Newton's third law makes that precise what the relationship is. The net force, or sometimes it's called the resultant force, or just the resultant on an object, just means the sum of all the forces. Well, each of these forces are vectors. That's why we bothered to define what the sum of a bunch of vectors was in chapter 3. We need to know how to add vectors. The x component of the sum is just the sum of all the x components, and the y component of the sum. So we'll sometimes talk about the net force on an object. A free body diagram is just a very crude sketch showing the directions and magnitudes of all the forces. Sometimes we won't know the magnitudes, but usually we know the directions of the forces with labeled arrows on it. So here was an example that you saw in the video where someone is sliding a really heavy box on the floor, and of course it doesn't keep going faster and faster. This person's pushing it at a constant speed. Why isn't it speeding up more and more? That's because friction is pushing back against the direction that the person is pushing. So there, in this case, the free body diagram, and we'll talk more about these as we go through, involves four forces. One is this person's pushing to the right, and by convention in free body diagrams, we always attach the force arrow with the tail to the object. And usually the object is just a blob, a box or something. Sometimes I'll label it with the mass of the object if we know it, just to help me remember what it is. So we've got the applied force being pushed to the right. I know it's a little small to see in the back there. The friction force, we'll find out, always pushes back against the direction. And when two surfaces are sliding against each other, the friction force on the sliding object is opposite the direction that it's sliding against the surface. And then there's a gravitational force. And if that gravitation, Earth is pulling down on this object, we'll talk about that later on. It's called the weight force. And if there weren't any upward force, that gravitational force would cause this thing to start accelerating downward. And so the floor is also, in addition to pushing back with friction, it's also pushing upwards normal, or normal means perpendicular to the surface that it's sliding on. So in this case, the normal force is upward because it's sliding horizontally. And let's just briefly go through Newton's three laws and some of the examples associated with them, and then we'll start doing problem solving, which mostly involves Newton's second law. But Newton's second law relies on Newton's first law and understanding of it. So we talked in the video, I'll just sort of explain this by looking at something. Maybe I don't need an object. I'm going to imagine I'm an astronaut in deep space, right? And here's an object, maybe a rock, and it's just floating in front of me. I'm not holding it, right? And I observe it like this, and I say, oh, zero velocity, zero acceleration from my point of view. That point of view, those statements are sort of connected to how I'm viewing it, right? So you here in the room would say, this has zero velocity. Now, if somebody else comes by in a spaceship and zooms by, right? They're just cruising through space. They don't even have their rockets on, right? They're just flying through space. They feel like they're perfectly at rest. They zoom by, they look out the window and they say, hey, there's something moving in that direction at 30 meters a second. So from their point of view, And there's no reason to argue that their point of view is less valid than our point of view, because in deep space, you don't really have a sense of whether something else is moving or you're moving, right? If you move at 50 meters per second in some direction, you still feel totally at rest. That's sort of an unusual perspective compared to here at Earth, where we're used to having something that we can always judge our motion with respect to, which is the surface of Earth. But the claim is it's true on Earth just as it is in deep space. If something's moving with a certain constant velocity and you observe an object, that's just as valid of a perspective to describe the motion from as one where the object's sitting at rest. A third person might come along and say, well, both of you thought this object wasn't accelerating. One of you said it had zero velocity, zero acceleration. The other one said it had a constant velocity, but zero acceleration. I might further observe it from a point of view where I'm looking out from my spaceship. I fire the thrusters behind me, and I start accelerating in this direction. I look out the window, and I see this object accelerating in that direction because I was accelerating in this direction. So this is all getting very confusing, and Newton's first law is meant to sort of constrain the ways we're going to agree to look at a situation. It still allows you to look at a situation from a lot of points of views, but this slide says, depending on how you look at it, an object might have many different velocities and many different accelerations to different observers. And that sounds like a complete mess. So Newton's going to say, in my first law, let's constrain it and agree to only look at systems from certain points of view, okay? Newton's first law states that it's always possible to observe events or an object from a point of view where every object with zero net force, that means if we add all the forces as vectors on the object and we find out they add to zero, the easiest way to get zero net force on an object is just there's no forces being exerted on it. Maybe it's in deep space, no gravity forces because there's no big masses near it anywhere, no electrical forces, no magnetic forces, that kind of stuff. So an object with zero net force on it will move with constant velocity. Now that wasn't true in the third case, right? I'm imagining we're in deep space, here's this object sitting in front of me. I'm looking around, no gravitational things pulling on it, no electrical charges nearby, no magnets, nothing like that. There's no way I can see that there should be a net force on this, and therefore it should move with constant velocity. When I look at it from the point of view of us here in the room, and I say it's moving with zero velocity is one case of constant velocity, right? It's constant at zero. Being at rest means constant velocity. That's one way that could have it. So that bit of evidence is showing me, yeah, it seems like I'm looking at it from the point of view of an inertial reference frame. That's what we call these. And I don't use too many abbreviations in this course, but I use the word the symbol IRF. Why am I? Oh, I see, I'm pushing the wrong button. There we go. IRF to stand for inertial reference frame. An inertial reference frame is one in which Newton's first law is true. So Newton's first law is saying you could always find a point of view, that's an inertial reference frame, from which this is going to be true. If there's no forces on an object, it should move with constant velocity. The second situation where there's no forces on the object, someone comes by in the spaceship with constant velocity and they look out the window and they say, that object has a constant velocity in that direction. Newton's first law seems to be satisfied there. We look around, there shouldn't be any forces on this object, and we'll find out a lot about forces in this chapter. No forces that I can see that should be on it, and it's moving with constant velocity in that direction. So it seems like Newton's first law is satisfied there. So that would be another example of an inertial reference frame, a different inertial reference frame. Whereas the third one, where the person is accelerating in this direction, looks out the window and says, there shouldn't be any forces on that object, but it's not moving with constant velocity, therefore it violates Newton's first law. That's an indication that the point of view of observing something from the point of view of that person who's accelerating to the right is going to be a non-inertial reference frame point of view. And we're going to find out that Newton's second law is phrased so that something is true only when observed from an inertial reference frame. Almost always when you observe things, you just intuitively tend to describe them from the point of view of an inertial reference frame. But you saw from the video, when you're orbiting the Earth in the space shuttle or something like that, things get a little bit weird. And sometimes when you're on a merry-go-round, a really fast amusement park ride that's going around in a circle, things seem kind of strange from your point of view, and that's because you're looking at them from the point of view of a non-inertial reference frame. Okay? So we just sort of take it as a warning. Now, most of the time, you're not going to run afoul of it. Most of the time, we do look at things intuitively from the point of view of an inertial reference frame. But occasionally, it should be in the back of our mind. All right. Oh, I probably put too many reading responses on here, but there are so many good ones in there. I can't quite read this here, but I understand the first law, but something about examples show an object never slowing down in the slightest bit. I feel like the example of air hockey isn't 100% frictionless. Well, that's true. There's still some friction. If you had a really huge table of air hockey, you know that thing goes at pretty much constant velocity until it hits one of the edges of the table. But if you had a really long run, it would eventually slow down because there's air around it, and when you're moving through air, the air doesn't slow you down too much, but it slows you down a little, and so that thing is actually not moving with constant velocity. That's not a violation of Newton's first law. We're still looking at it from an inertial reference frame. It's just that there is a net force on it. It's the air resistance pushing back against this thing. So it's not moving with constant velocity, but it also has a non-zero force on it. Other people mention deep space, and deep space is a good example where we really believe if there's no particles of atmosphere around, so there's no air resistance, you're in deep space, there's no gravitational force or anything like that, and you start moving with constant velocity relative to something else, maybe relative to an asteroid, you're just going to keep moving. And if you wait a year and check, you'll still be moving with the same speed in the same direction relative to that asteroid, assuming the asteroid didn't have any forces on it itself. So deep space is a good example of a truly frictionless environment. So an object is at rest is not the natural state of the object. Moving at a constant velocity is the natural state. This is so backwards to what I always thought. What do you say to that? That an object at rest is not a natural state of an object, but moving at constant velocity is. Is there a contradiction there? It sounds like there's a contradiction, but there's not. I mean, I would say the first sentence is not true. An object at rest is just as much of a natural state as moving at constant velocity, because if you're at rest, you have a constant velocity. It just happens to be 0. But 0 is a good constant number, just like 1 or 2 is. It's not changing. Your velocity is 0, then it's 0, then it's 0. So, and it's easy to forget that. Constant velocity can just mean forever at rest. If there are a number of different velocities and accelerations for an object, will there ever be more than one inertial reference frame? Well, yes, we just gave an example of 2 inertial reference frames from which we could observe something in deep space, and clearly there are going to be an infinite number of them moving at different speeds with respect to that object, different velocities. So there are always an infinite number, although usually there's kind of only one that makes sense for a problem. So don't feel like you're going to have to choose among an infinite number of things every time you do a problem. Usually we'll all just naturally choose one IRF without thinking. When the hammer is dropped, this was in the space shuttle example where you're orbiting Earth and it appears to have no acceleration to the person inside, it goes into orbit at constant velocity, right? Thus, because it appears to have constant velocity from both Earth and inside the shuttle, can it be assumed that the hammer has no net force acting upon it and that both reference points are reference frames are IRFs? Here, anybody have a comment on this one? There is a statement in here that sounds reasonable, but is false. I think the conclusion they're trying to make would be true, but the statement that came before it is false. Caitlin. That's right. It's, you know, in everyday language, sometimes we conflate the ideas of velocity and speed. Speed means how fast something is going. And when something's in a circular orbit around Earth, generally it's going at a pretty constant speed, as long as the orbit is circular. If it becomes non-circular, that's not true anymore. But, you know, we try, when you have the space shuttle going around the Earth, it's trying to maintain a certain constant altitude, so its speed will be the same. That doesn't mean its velocity is constant. The velocity is a vector, and that vector is changing as it goes around. So this is not a case where something has constant velocity. It definitely doesn't have constant velocity, and that means there's got to be a net force on it if you're observing it from an IRF. So when we look at the Earth, we sort of pull back from the Earth and you know, look at the sphere of the Earth over here, and we see it going around. I'm saying, I want some evidence that tells me I'm in an inertial reference frame. In an inertial reference frame, non-zero net forces should be associated with acceleration. Zero net forces should be associated with no acceleration or constant velocity. Here's something that definitely doesn't have constant velocity. There's got to be some sort of net force on it if I'm observing it from an inertial reference frame. And that is a kind of inertial reference frame when you pull back above the Earth. Okay, last one. I understand that Newton's first law relates to the inertial reference frame. So is the inertial reference frame whichever point of view makes Newton's first law true? That an object is at rest or at a constant velocity as long as no net force acts on it? I'm not. Oh, if not, I'm still a bit confused as to the relationship between Newton's first law and inertial reference frames. I'm forgetting exactly why I put this one on here, but I think it's sort of asking about still that there are more than one inertial reference frame that we can always observe any set of events from and will satisfy the conditions of Newton's first law. So there's always a lot of different ways we can view it, and that things will have different velocities. That's okay. Newton says it'll all still work out. I was just going to say something else and it evaporated. I guess I was going to say, well, you know, how do you look for evidence that you're not in an inertial reference frame or you're in a non-inertial reference frame? You're always looking for objects that either have no net force on them and seem to be accelerating from your point of view. And you've got to kind of know what forces could be acting on it, because some of them are like gravity. They can act at a distance. They're kind of invisible forces, but they're still pulling. Or things that have have a non-zero force, net force on them, and still somehow move at a constant velocity. If either one of those is true, it seems to be evidence that you're in or observing from a non-inertial reference frame. I know this seems a little bit excessively confusing, but you know, it's crucial for Newton's second law, which we're going to go to later, but it's not as damaging to us as you might think, because most of the time, you know, when we're here on Earth sitting in the lab doing an experiment, we're going to be observing from an inertial reference frame. So in most cases, it's not going to be such a tough call. And if you really start thinking about the notion of inertial reference frames, it's really easy to go down some philosophical hole where you say, but how do I really know that there are no net forces on it? Maybe in some weird way, the object I'm watching and I'm moving along with it, and we're moving in some really weird way together, and I see it at rest, and how do I know that that's not the case? And those are good questions, but we just don't have, it's not usually the subject matter of an introductory physics course to think about that from such a deep level. Okay, so now on to Newton's second law. Newton's second law refers to the mass of an object, and it's worthwhile talking about the notion of a mass of an object because we usually confuse it with the notion of weight. So mass is not the same as weight. Something can have zero weight, but a non-zero mass. For example, here's a ½ kilogram brass mass. I can feel the weight of it. The weight means, we'll talk about this in a second, the gravitational pull. It's a force, the force of gravity on this. And I have to push upward on it to counteract the gravitational force from the Earth on it. So it has a weight here. It also has a mass. Mass, I say here, is a measure of resistance to the state of change of motion. Resistance to change of the state of motion of an object. That means changing its velocity. So if something has a large mass, that means it's really hard to change its direction. So if this thing's floating by in outer space, If I flick it with my finger, if it was made of styrofoam, it would be really easy to shoot it in that direction with a little flick, right? But if I flick it, I'll hurt my finger, and it will pretty much keep going in the same direction because this is a pretty substantial mass. That's the measure of mass. Something could have a lot of mass but no weight. For example, this might have a substantial object in deep space. There's no gravitational forces on it, so we would say its weight is 0, but it still has a substantial mass. So if someone hands you a rock in outer space and you want to know, is it a fake styrofoam rock or a really dense rock that's made of some heavy minerals, you can't put it on your hand in deep space because you're not going to feel any force. There's no gravitational force pulling it down against the force of your hand. Regular scales don't work. But you can always take the object and try to accelerate it or shake it like this. I'm accelerating it when I shake it back and forth. And that will give you a sense of how massive it is, right? I'm accelerating it this way, then accelerating it that way. And the harder it is for me to do that, I can feel that pressure against my skin. The harder it is to do that, the more massive it is. So that's just an intuitive notion of mass. Mass and inertia mean the same thing. So an object that's very massive has a lot of inertia. They're really just two words for the same thing. So Newton's second law is phrased in terms of an IRF. Only when you view an object or a series of events from an IRF is the following statement true. The net force on an object, or I should have probably written this the way that Giancoli does. He writes the net force with a sigma symbol. Those of you who have taken a calculus course before might have seen this symbol, capital sigma. So, well, maybe at first Giancoli might write it this way. This means the sum, it's shorthand for the sum of all the forces. Sigma in mathematics usually means sum them all up. So we're summing up all the forces acting on an object, and that's equal to the mass of the object times the acceleration of the object. So in other words, the acceleration is going to be in the same direction as the net force on the object. I sometimes write this as F net. F net and the sum of all forces mean the same thing. That was the definition of net. But I've noticed that Giancoli tends to use sigma, so I'll try to use sigma just to match him. Here I've written F net. So F net equals ma. If there's a whole bunch of objects around, that's true for every individual object. Maybe you got several objects colliding, right? It's true at all moments. So when these two objects are coming towards each other, maybe there's no forces on them. This one has no net force on it, so it's moving with constant velocity. This one has no net force on it, moving with constant velocity. When they hit each other, they do have forces on each other. This one feels a force from this one, so this one has a net force on it. If the net force is in that direction, it starts accelerating in that direction. And so when they come together, maybe it goes off in that direction, and same for the other one. So there could be lots of objects, and there can be, each object is going to have its own acceleration. But notice, related to what I said yesterday, there's only one acceleration for an object at every instant in time. There can be lots of forces acting on it, right? Just like that box where the guy was pushing it. There was a friction force, the applied force, the normal force, the weight force. There were lots of forces, but only one acceleration at every instant in time. And the SI unit of force we can get by, well, we already know accelerations. SI units are meter per second squared. Mass's SI unit is kilogram. We talked about that the very first day. And therefore, the SI unit for force is going to be kilogram meters per second squared, but the shorthand for that is Newton. So we're going to measure our forces in newtons. Okay, I think we're almost to starting some examples, but I tried to throw in some of these that had to do with the section we're in as we went along. Maybe too many reading responses. I like them, though. They're fun to read. Why in the book does it refer to Newton's second law as F equals ma with a sigma sign in front of it? Okay, I think we talked about that one, but if anybody has another question on that. Sigma just means sum up all the forces on that object. Why does it matter that you need to add up all the forces if it is just one? Well, when this means add up all the forces, if there's only one force acting on it, this is just one thing here. If there are two forces adding on it, you've got to add up the two forces. If If there are 3, there would be 3 things here. If there are no forces, this would just be a big 0. There's no force on it. In Newton's second law, I was confused as to what it meant when it said that it would be inversely proportional to mass. How would this be shown in a real-life scenario? So the inversely proportional mass means that if we solve for acceleration, right? I erase that. One of my red markers over here left a stain on the board, so now I'm afraid to use red markers. If we solve for the acceleration, that means it's equal to the sum of the force vectors acting on it divided by the mass. So we would say acceleration is inversely proportional to mass. If mass gets big, acceleration gets small, given that the forces are the same. Right? So if I've got an object and I imagine this object is either really massive or maybe it's just a fake and it's actually hollow, so it's not massive at all. And I put a certain 1 Newton force on it. When the object is really massive, the acceleration will be small. Big mass means small acceleration. If I put the same force on it, and this is faked up, so it's empty on the inside, not very massive, the same force will produce a huge acceleration, right? So big mass, small acceleration, that's all that means. Even when something's not moving, like a wall, can it exert a force? How is this possible? Is it because the structure of the wall is stronger than ice skater running into it? Yes, an object that's not moving, someone else mentioned that, I didn't realize that not inanimate objects could exert forces, but that's, all sorts of things. Any sort of object can exert a force on another object. It doesn't have to be a living thing, doesn't have to be animate, it doesn't have to be moving. When I slam my fist down on here, I'm exerting a force down on the table, but the table is also exerting a force up on my fist. That's why it hurts if I slam it hard enough. Okay. So the remainder of the chapter, I know this is sort of obscured by my sharing the screen there, is just going to be us investigating different kinds of forces. So far, we don't really have much detailed knowledge about forces, so we've got to figure out all the forces that might go into here. Once we've got some forces, we can calculate an acceleration. And once we've got an acceleration, if the acceleration is constant, we can go back to our good old friend, kinematics. And in most cases, you'll find it's actually constant acceleration kinematics in 1 dimension. So we'll get to practice that a lot more as time goes on. So the first force we're going to describe in detail is the weight force. The reason people conflate the idea of mass, which here is given by the symbol m, and weight, given by the symbol w here, is that on the surface of the Earth, they're proportional to each other. If you double the mass of the object, its weight's going to double, and that's why scales work. We can just calibrate them so that they divide by the appropriate factor and give you the mass. But this little g has magnitude 9.8. It's a vector because little g is the acceleration magnitude. The direction of the free fall acceleration is in that direction. So we can actually visualize little g as being a vector. Near other planet surfaces, little g is going to have a different value. So that 9.8 is specific to being at the surface of Earth. Okay, on to the third law, and then we'll get to some calculational examples. I think I said this in there in the video that if I pull on a door handle, the door handle pulls back on me, and Newton's third law just makes that precise. You can't exert a force on something else without it exerting a force on you, and that's true even for 2 inanimate objects that are pushing on each other. When one pushes on the other pushes on the one, and Newton's third law tells us, well, exactly how do those 2 forces relate? When 2 objects, call them here A and B, interact, the forces they exert on each other are equal in magnitude and opposite in direction at every time, no matter what. So those forces might be changing. 2 objects coming together, their force on each other is 0. So they're equal and opposite. Then they exert a little force on each other. This one exerts a force in that direction on this one opposite force in that direction. As they start really pushing against each other, maybe they're squishing a little bit, the force vectors get huge, but they're always equal and opposite. Okay, so that means if I draw the one force vector on B, the force on B by A is always in the other direction. So they're related by a minus sign. Okay, and then to use Newton's second law to solve, Newton's second law, we're not used to, perhaps in Physics 110, writing down equations that have vectors on both sides. But all that means when I have a vector equation is that in order for two vectors to be equal, that means the x components have to be equal, the y components have to be equal, and the z components have to be equal. And in order to know what x, so we're going to use these to calculate these three equations, maybe just two of them in some situations. In order to know what they mean, we need to draw the axes on a little cartoon of the situation. And that's what you saw in the usual cartoon I'll use is a free body diagram. We need to say what x and y mean. Okay, first example that you saw in the video involved a crane with a cable lifting up some beam. The beam had a mass of 185 kilograms, and someone measured the force that the cable was exerting upward on the beam. You could attach something in the middle of the cable, just like those fishing scales, right, where you hold the fish and it tells you the weight of the fish. That's how much force you're having to use to hold it up. So in this case, somehow we know it's 1,960 Newton cable force pulling up on a beam. And the question is, find the net force magnitude on the beam and the resulting acceleration. And to do all of these problems, we've always got to get in the habit of drawing a free body diagram and choosing axes. I always draw my axes right next to the free body diagram. And then once we know what x and y mean, we can do F net x, or the sum of the force x components, equals max, and hopefully solve for ax. And same thing for y if we need it. So I've drawn a free body diagram here, right? Here's the beam. Someone told me the cable's pulling up with 1960 newtons, so I put that on there. And if you're at the surface of Earth, Earth always pulls down on you with your weight, and your weight can be calculated by mg. So if this is a 185 kilogram mass, then here's my m, and here's little g. The direction is down, but this is how long that vector is. Okay, that's free body diagram, and for some reason I chose plus y is up. I could have put an x-axis on here. In this particular problem, x isn't very interesting. So we're going to do the sum of the force y components. And when I do the sum of the force y components, or I wrote it as F net y, that's, let's see. This vector has a positive y component because in going from tail to tip, it goes in the positive y direction. So it comes in with a plus sign, plus 1960. Whereas this vector, whose length is mg, comes in with a minus sign because it's pointing in the negative x direction. So that's why I put this minus sign right there, minus whatever the result of the calculation mg is. So that's the sum of the forces right there. And I'm going to set it equal to MAY, sum of the force y components, and I could then solve for AY. And in this case, we'll find that it accelerates upward at 0.785 meters per second squared, quite a bit less than free fall rate. And if you had done the x components, you would find out that the net force x component was 0 and ax was 0 as well. There's really nothing going on in that direction. Then part B is asking us to do a little kinematics calculation. If it begins at rest, we now know its acceleration magnitude. How far upward has it moved after 3 seconds? That sounds like we want to know y versus t. So we grab the y versus t equation and do a quick calculation. It's a one and done, 3.58 meters that it moves in those 3 seconds. All right. Let's practice. What I'm going to do is, as we go through these, I'm going to have us do similar problems that involve similar forces. Here's something that feels a little bit different. We're looking at problem 1 on here. 5 kilogram block is given a push on a horizontal frictionless surface so that it initially travels with a constant velocity of 3 meters per second. So maybe it's on an air hockey table on the left-hand part here that's labeled as frictionless. It's moving at 3 meters per second. And all of a sudden, it runs into a part of the table where there's no air blowing up, and all of a sudden there's some friction. And the friction force, we're told, has a magnitude of 14.7 newtons. You don't need to really know anything about friction here other than the friction force is going to be direction opposite the direction the thing's sliding. So if it's sliding in this direction, the friction force being applied to it is going to be opposing its motion. So in this diagram, it would be acting to the left. Find the magnitude of the acceleration. You're going to want a free body diagram of the object. And also find how far into that friction region it slides before coming to rest. That sounds like a kinematics add-on problem. Yeah. You don't have to. Now, it would be easy to conclude that they're equal because it's not accelerating along that direction. Initially, it's at rest. If it started accelerating, it'd be blasting off or burrowing into the plane. So since it's not accelerating, the y components of the forces have to cancel. The ones horizontal don't have anything to do with it. So that means these only two vertical ones better be equal and opposite to give zero net force. But it doesn't really matter so much if you're drawing the arrows exactly the same length, although if you know they are, it's a good idea to draw them the same length if you can. Just for reference, I got 2.94 meters per second squared. And for part B, 1.53 meters. Anyone having trouble getting started? Yeah, so one problem is you don't have any axes put next to your free body diagram. So that's one of the, as soon as you draw your free body diagram, you need to know what x and y is, because we're going to write down the sum of the force x components equals max, and the sum of the force y components equals may. Now in this case, it's pretty clear the y direction is going to be uninteresting, so let's focus on x. Now, what I see this one is the friction one because it's labeled with the appropriate force. What's the one going to the right? What is that force going to the right in your diagram? It would be what? I couldn't hear that. Well, movement isn't a force, right? So when something's in empty space, right, it'll just float along relative to you. It doesn't need any forces, right? It just keeps going happily. That's its natural state. So we don't need any forces to be going forward at 3 meters per second. And so in this case, there aren't any. Just because something's moving doesn't mean there's a force on it. And that's kind of disagrees with our everyday intuition, because on the surface of Earth, there's always so much friction that we have to kind of overcome it at every moment to get something to move. Okay, let's start out by doing a free body diagram and attaching some axes onto it. In this case, when I draw a free body diagram, I'll just label it as FBD for it. The only object of interest here is the 5 kilogram object. And just so that I can remember what that blob means, if I know the mass of it, sometimes I'll write the mass of it, and that way I'll be sure. But you know, we might have a 5 kilogram object and a 7 kilogram object in some problem. We want to know which object that we're talking about. So I'm going to write its mass in the middle of it. And we're asking ourselves what forces are on this as it's sliding to the right and enters that friction area. Well, one of them is this friction force. What was the magnitude? 14.7 newtons. So there's a force going to the left as it's sliding to the right that has magnitude 14.7 newtons. It's near the surface of Earth, so of course there's a weight force, and I know how to calculate the length of this weight force vector. It is the mass of the object times little g. So the length of that vector is 5 times 9.8. That's just mg, and that was the formula for the weight of an object near surface of Earth. There's also got to be, and I think at this point in the video I had talked a little bit about a normal force. I'll write it as Fn. I think that's how Gianculli denotes it. A normal force up from the table, because if this force were not opposed by some other force, there would be a net force along this direction, and that would cause this object to accelerate along that direction. And that would mean if it were sitting originally at rest on the table, an acceleration in that direction would cause it to start blasting off vertically or burrowing into the table. We know it's not going to happen, and therefore the net force has to be 0. So those two forces are going to balance each other. We'll be able to see, and we could even justify that later on. The important thing is that there's no force in this problem going to the right. It is moving to the right, but just because something's moving to the right doesn't need a force to do that. When something's in empty space, an asteroid floats by you like this at constant velocity, it doesn't need a force. It feels like it's totally at rest. You feel like you're at rest, and it feels like it's at rest, and you're both right in some sense, or neither of you are right. There's no such thing as absolutely being at rest or absolutely moving. It's just relative motion. So those are the only forces that I can see acting on the object. And well, now I need to put some axes on it in order to use Newton's second law. So my next task is to attach XY axes. One of the rules of thumb that we're always going to use is if I know the direction an object is accelerating, I want to have one of my axis directions be along the direction of acceleration. I know I said this several times in the video. And that's just going to simplify our life, because then if we know, well, which way is this object going to be accelerating? We kind of know what its motion is going to be, right? It's slowing down in this direction. So that's back to our old one-dimensional motion kind of stuff. If something is slowing down as it goes to the right, which direction is its acceleration pointing? Yeah, it's going in the opposite direction, right? So if this is plus x, I haven't put an x coordinate system on there, then ax would be negative, right? So it's accelerating towards the left. So I'm going to take one of my axis directions. Maybe it doesn't really, I don't have to do it exactly along there. I could have done it the opposite direction, but in this case, let's take plus x to be to the left and plus y to be up. You may not have chosen that convention, but there's nothing wrong with it. Okay, I've got my free body diagram, I've got my axes, and now I'm ready to do F net x, or sum of the force x components equals max. We can even do sum of the force y components equals may, just to see what we get out of it. Just like with the kinematics equations, I'll always write the generic form first when I'm in front of you, and then fill in the details as we go down below. So on the left-hand side, we've got to add together all of those forces that are acting that have non-zero x components. So let's go to Fn. What's its x component? It's 0, because in going from tail to tip, I only need to move along y. I don't need to move along x at all. That's what Fx meaning is 0 means. Same thing for the weight. In going from tail to tip, I don't have to move along x. It's all along y. So the sum of the force x components is only going to have one thing, and it's a negative x component because, oh, I'm sorry, in my coordinate system, it's positive. In going from tail to tip, I move along my positive x direction. So this is going to be a positive contribution, and that force size is 14.7 newtons. So that's the only thing that comes in the force sum on the left-hand side because we're talking about x components. We'd have more than one thing if we were talking about y components. The m here always refers to the mass of the object in the free body diagram. So that's 5 kilograms here. And again, I'm going to be lazy and not put in the units because we're putting in all SI units. And so when I solve, I can just get the SI units I'm looking for. So that means AX is, well, if I solve, AX is 14.7 over 5. You put that in your calculator, 2.94 meters per second squared. AY is 0. Again, I can see AY is 0 because moving along this direction, if AY were not 0, it would start blasting off vertically or burrowing down vertically. It's clearly not going to do that. So I know that's why I chose my X to be horizontal. So to answer the question, the magnitude of the acceleration, right? The magnitude of the acceleration is the square root of, you don't have to write this down, but that's how in general we calculate it. But AY is 0, and the square root of AX squared is just the magnitude of AX, 2.94 meters per second squared. Had you chosen your plus x to be in this direction, then you would have, or should have, gotten a negative AX, and that would be fine. The magnitude of the acceleration would still come out without a minus sign in front of it. Is that all I asked in A? Find the magnitude of the acceleration. Yeah. Questions on A? Again, I furiously am writing these up and calculating things before class. I'll scan them in and post them on the website. That's what I'm trying to do every day, so we have lots of things to refer to. Okay, and then in B it says, how far does it slide before coming to rest? So it's happily moving along in the friction region, then it hits the friction full region, and it slows down, and at some point it comes to rest. It's apparently slowing down with constant acceleration, right? Because this is the same force that was acting all the way through the motion. It's a constant friction force, and therefore we're finding out the acceleration is constant. AX is constant, so I can use my constant AX kinematics. Which, if I want to know how far it travels before coming to rest, which of those three equations, Vx versus t, x versus t, or the Vx squared equation is going to get me directly to the answer of how far it travels before coming to rest? Well, yeah, I think I want to avoid t because I don't know anything about the time, and I don't want to know anything about the time. I'm not saying you can't get there, but you're going to turn a one-step problem into a two-step problem. Not the biggest deal in the world, but still, I would have to find t in order to figure out what x is if I wanted to use the x versus t equation, right, to calculate x. Rather, I'm going to first gravitate towards this one, which has the squares. Vx final squared equals Vx initial squared plus 2ax times delta x. And that delta x means how far it moves, what its displacement is in between initial to final. So this is what I want to find. And it looks like I know everything else in here. If initial is when it first enters the friction region, final is when it just barely comes to rest, Vx final would be 0. Vx initial, was it 3 or something like that? Yeah. And we found out now that, well, let's see. I guess I better be careful about these components here. In my coordinate system, AX is going to be positive, right? If I'm going to stick with this coordinate system when I'm writing down this kinematics equation. You don't have to. I could have changed my mind as long as I put the correct signs in. But just for the sake of argument, my AX is positive 2.94. What am I expecting for the sign of delta X in my coordinate system, Sam? Oh, okay.
So would that make the initial velocity -3?
Yes, the initial velocity is -3. Now that doesn't come to anything because we're squaring it here. But you're right. If you used it in another equation where it weren't squared, you better put it in that minus sign. But here, yes, the initial velocity is -3 in my coordinate system. Doesn't change it when you square it. Okay, so it's this times delta x. And when I solve for delta x, I get something that's negative, right? This thing is positive after you square it. I bring it over here and it's negative, so I've got a negative number. And then I divide by this positive number here. A negative number divided by a positive will be negative. So my delta x is negative 1.53 meters. Now, if somebody asks you, how far did it move? Nobody usually gives a negative answer there. So if you're answering this, it would be sensible to just say 1.53 meters. But in my coordinate system, the displacement is that. Questions on that or other alternative methods that you wanted to do that did or did not lead to the same answers? All right, good. That was somewhat simple because it only involved, kind of one obvious object that we might have. Come on, share screen. That we might have applied a free body diagram to in Newton's second law. I think I clicked share screen and I'm just, there we go. I think this computer needs an upgrade here. All right. Here is a second example, and this is where things start to get confusing. So we're going to do a couple of examples related to this one. But let's just very quickly look through the solution you saw on the video. 80-kilogram man in an elevator stands on a scale that reads in Newton. So I didn't draw a cartoon of it, but I did draw a free body diagram. Here I am in the elevator, and I'm standing on a scale. And I'm going to draw a free body diagram for me. You might have gotten confused and said, I'm going to draw a free body diagram for the scale. Unfortunately, you'd pretty quickly realize you don't have enough information to do much with it because I have no idea how massive the scale is, and therefore I don't know how much the Earth is pulling down on it, which is going to relate to how much the bottom of the elevator is pushing up on the scale. But for me, 80 kilograms, I kind of know the force that's pulling down on me because I know my mass. Okay, so we want to know what the scale reads. And the scale force on me, right? I'm standing here on the scale. The scale is supposed to read how hard I'm pushing down on it, right? The magnitude of my force on the scale. What I'm going to find instead is the magnitude of the force that the scale is pushing up on me. Why am I justified in saying that's the answer? That's not how scales are designed. Scales are designed to read out what is the magnitude of the force the object on top of them is pushing down on them with, right? Hopefully that makes sense. What I am going to find is how hard the scale is pushing up on me. What principle tells me that those two are the same thing? Andre? It's actually Newton's third law, but it's easy to get them confused. The one that says the equal and opposite force, right? If I push down on a scale with a certain force, the scale pushes up on me with the same magnitude force. So if I can find the magnitude of the force that the scale is pushing up on me with, I know that's how hard I'm pushing down on the scale, and that's what scales are supposed to read, right? They're measuring the weight force that's being pushed down on the scale. So here's a free body diagram for me. I'm 80 kilograms. Of course, always, if I'm near the surface of Earth, I have a weight force. Its magnitude is 80 times 9.8. If there weren't any other forces, I'd be in free fall, right? So there's got to be something else holding me up, and that's the force up from the scale. And I decided to take plus y up. You could have put an x-axis in a perpendicular direction, but again, this is a problem where nothing interesting is going on in the x direction, so we wouldn't use that x direction. But just using the sum of the force y components equals MAY, the elevator stopped and just sitting there, and that means me, the object of the free body diagram, has zero acceleration. So my y acceleration component in particular is 0. So the right-hand side, MAY, is just going to be 0. The left-hand side is where everything's going on. In my coordinate system, F scale comes in with a plus sign because it's pointing along the plus y direction, and the 80 times 9.8 comes in with a minus sign. We're talking about y components here, and y components have plus or minus signs that you got to think about. That allows us to solve for how hard the scale is pushing up on me, which I know that's what the scale is going to read by Newton's third law. Okay. If the elevator is moving up at 6 meters per second instead of being at rest, what changes in this argument? Without me clicking forward, because you've watched the videos where we talked about this. I was at rest in the elevator. Now the elevator has sped up to a constant speed of 6 meters per second upward. What in this calculation or in the picture is going to change? Well, nothing's going to change in my free body diagram because by virtue of being near the Earth's surface, my weight is going to be mg. Doesn't matter if I'm moving up, moving left, accelerating up, spinning in a circle, my weight is what it is, right? The Earth's always pulling on me in that direction with magnitude mg, where m is my mass. So this isn't going to change. We didn't make any assumptions about the scale force before, so that's just so there's got to be an upward scale force when it's going up, otherwise I'd be in free fall again, which I'm clearly not if it's going up at constant speed. So there's some scale force, maybe we'll solve for it again. If we're moving up at a constant upward speed of 6 meters per second, what's AY in that situation? It's 0, so AY is still 0. So the whole calculation looks exactly the same, and the answer is the same. Whether or not the elevator is sitting still or moving up at a constant speed or moving down at a constant speed, the answer is the same. The scale reads the same, and you'll actually feel the same. In the same way when you're in outer space, you don't know whether you're moving in this direction or upwards or downward at a constant velocity. There's no way to tell. All of those feel just like being at rest. It's the same way here. We don't care how fast you're moving. What we care about is different accelerations, but this is a constant speed, and therefore the scale reading is the same. And I will feel in every respect the same, except there's probably some vibration in the elevator, but we're ignoring that. Okay, so now let's change it. The elevator is accelerating upward at 3 meters per second. In this case, the free body diagram looks exactly the same. Even if I'm accelerating upward, my weight is the same. It's mg. That's how we always calculate it near the surface of Earth. There still is some unknown scale force if I'm accelerating upward. So this looks exactly the same, and I'm going to make the same assumption about plus y direction. It's this that changes. AY is not 0 anymore. When I do the sum of the force x components, that part looks, or sorry, sum of the force y components, that looks the same. But now AY is plus 3, because plus is up and we're accelerating in the upward direction. So AY is plus 3. M is the mass of the thing in the free body diagram always. This is F net equals MA, and I can solve for the F scale. F scale, before we had a 0 over here, and we just brought the 80 times 9.8, right? We got 784. Now we're going to have 784 plus something extra. The scale reads more, and you have some intuition probably about that. Most of the time when you're riding in an elevator in a skyscraper kind of building, it very quickly accelerates, and then it goes at a constant speed most of the way, and then it very quickly decelerates as you get to your floor. But in that when it first starts going, there's a moment where you just kind of feel heavy for a second until it gets up to speed. Then you feel normal, other than the vibration. And so this is saying, yes, not only does the scale read more, you feel like you're heavier. That doesn't mean you are heavier. Your weight is what it is. Your weight's still mg. It hasn't changed. But sometimes people say, your apparent weight is bigger. That means that you feel like you have a larger weight. And the scale is one way to sort of measure how heavy you would feel. And finally, in D, the elevator cable breaks. Everything's in free fall. What does the scale read? Most people have the intuition that it ought to read 0. You can actually show that that's true using Newton's second law again. In this case, the left-hand side, we don't know. Maybe there's an F scale. I'm going to put it in the upwards direction and just solve for what it is. Now, if I'm in free fall inside the elevator, which is in free fall, my AY is minus 9.8. And notice that this term cancels exactly against that term, leaving me with F scale is 0 newtons. And most people have that intuition, but it's nice to know that you can show it from Newton's second law as well. Okay, 2 more quick reading responses. I understand the concept of an FBD, but are we supposed to always assume the normal force and little g are balancing each other out? Are there other forces that should be second nature for us to place on an FBD? Not at the beginning. There's none that are going to be second nature. They're only going to get less familiar as we go on. Weight, most of us kind of know some stuff about, but if I were to, I want to address the first sentence here. Are we supposed to always assume that the normal force and little g balance each other out? There's something that just doesn't make syntactic, well, it doesn't make sense in that first sentence. And a lot of times people say things and they mean something that they aren't saying. But here, what is being said? If we take it literally, why would I not say that the normal force and little g balancing each other out makes any sense? Right. So a force can balance out a force. Little g has units of acceleration, right? It's a kind of dimensional object, which is an acceleration. Accelerations don't balance out forces. Forces can balance out forces. So I think what the person means is the normal force balances out little m times little g, right? Those two forces usually balance each other out. Is that always going to be true? Well, no, it's not always going to be true. Here's a mass here. Its weight is what it is. I think it's a ½ kilogram, so it would be 0.5 times 9.8 is its weight. When I have it sitting on the table there are 2 forces on it. Earth's pulling down on it, and the normal force from the table is pushing up on it. It's not accelerating, so those 2 must balance out. If they didn't balance out, if the normal force were bigger, there would be a net force in that direction. It would start blasting off, right? If the weight were bigger, it would start burrowing into the table. So they're balancing each other out. I can make the normal force bigger just by pushing down on it. That doesn't mean the weight is the same. The weight of this object is the same, but now there are 3 forces acting on the object. There's the weight force, the table's pushing up on it, and my hand's pushing down on it, and all 3 of those have to add to 0. And the way they add to 0 is the normal force. You probably have the intuition that the normal force is getting bigger. I'm causing the table to have to push up harder when I push down on it. So we can't always balance those out, although in a lot of situations, things will just be sitting like that. But you don't want to always assume that, because then as soon as you do, up will come a problem where some other force, and we will see problems later on where, you know, someone's pushing a sled along, but they're actually pushing down at an angle. And so they're partially pushing down into the ground, and it's like me leaning on this. You can't just assume that the normal force equals the weight force in magnitude, always. On page 79, the book says to be careful when we use on and when discussing the force exerted. Yes. In my example of me standing on the scale, there's a force of my force on the scale exerted by me, and the force the scale exerts on me by the scale. It's hard to even say that, but we will find out that it's extremely important to know, you know, for example, when I am drawing a free body diagram, all of these forces should be forces that are on this object. If this object is exerting a 7 Newton force on something to its right, that doesn't belong in this free body diagram. These are only forces that are on this object. So you do have to be careful, at least at this point, that you're only putting in forces that are on the object that's at the center of your free body diagram. Okay, here's some more practice with the elevator kinds of concepts. So I think it's similar enough that I'm going to have you just go through problem 2. And if you're really fast, you can try 3 and 4 as well. But Yes, the scale is supposed to read in newtons. I should have said that. Thank you, Noah. You know, here in the US, our scales usually read in pounds, which is a force unit from the English system of units. But I believe if you're in Europe, your scale would probably read in kilograms, which is a mass unit. So the scale is actually doing that conversion because weights and masses are proportional to each other at Earth's surface. I'm just flipping back here to this slide in case somebody wants to reference it in doing their work there. So again, if you're having trouble getting started on any one of the parts, feel free to raise your hand. Normally, you would have a partner right next to you in any other semester where you could at least ask them first, but unfortunately, our what would be group work is more silent work. Yeah, you should be using Newton's second law, and the calculation looks just like the one here. Just this number changed here, right? We're going to write F net y equals MAY. Did you draw an axis on your free body diagram? Yeah, plus y is up. So now let's do the sum of the force y components on the left-hand side equals MAY on the right-hand side. No, when we say the sum, we have to put in the signs for the component. So look over here. The scale, we have two forces, right? This one, these are components, right? That's why there's a little y right there. So this has a positive y component because it's going in the plus y direction. This one has a negative y component because it's going in the minus y direction. So when I'm doing components, the F scale comes in with a plus sign because in going from tail to tip, we go in the plus y direction. That's what a plus component means. This one comes in with a minus sign. And most importantly for this, and it's same for part A there, I think the elevator stopped at the beginning. That means the acceleration is 0, and certainly that means the y component of the acceleration is 0. So the right-hand side of F net equals ma equals 0, and that means the scale force minus the weight is equal to 0, and therefore the scale force equals the weight. Yeah, some of these at the beginning, they're simple enough that you might be able to do them without going through the formal procedure of Newton's second law. Don't fall prey to that because they will very quickly get so complicated. You need to be used to free body diagram, axes, and then F net equals ma. So when you say, what is this object that you're drawing there in the free body diagram? Is it the person, or is it the scale, or is it the elevator? Yeah, because there's no way to know what the forces are on an object if we don't decide what the object is. So one problem you'll run in with the elevator right away is when we use F net equals ma, the F's that we're using are forces on that object. The m is the mass of the object. We don't know the mass of the elevator. Presumably it's got some huge mass, right? because it's a huge chunk. Oh, the woman's mass, isn't that right? Yes, 55 kilograms. So I would tend to just say, well, let's try a free body diagram for the woman. That means we're looking for forces that are acting on the woman. So I tend to write a little 55 inside that block. And that reminds me, oh yeah, okay, this is a 55 kilogram mass. And what are the forces on the woman? Well, she's in an elevator. She's accelerating or not, she's got her normal weight, and that's just mg. So there's an mg going down, a vector of length mg going down. And what else? If you're standing in the elevator, whether it's accelerating or not, what other forces besides the gravitational force pulling down on you do you feel on you? Well, just like right now, I can feel the floor pushing up on my feet. In this case, that's the scale pushing up on the woman, right? So we would have an F scale going up. I can't quite read what this third one says there. Yeah, so there isn't a separate force that's just for the acceleration. We would say there are a bunch of forces, and what they...
It's the force or the acceleration times the velocity's.
Yes, so we're not going to think of that as a force. Like all the forces belong on the left side of F net equals ma. And then the ma we're going to think of as, oh, that tells us about the acceleration that results from all those forces. But this side is not a force by itself. It doesn't belong in the free body diagram, right? I had these two forces here. The may was 0 here. That didn't appear as a third force over there. Even if it were non-zero, it wouldn't appear as another force. So ma is not a force. All the forces belong in the sum of the force thing on the left-hand side. And when something is accelerating, yes, I know there's got to be forces on it, but that doesn't mean that that acceleration is a separate force. It doesn't belong in your free body diagram because it's not a force. So I think you want to erase this third arrow there. There are only two things, just like when I'm standing here, there are only two things exerting forces on me. Gravity's pulling me down and the floor is pushing up on me. When I start accelerating upward, I feel those forces change, right? I feel a bigger pressure on the bottom of my feet. But that doesn't mean another force has appeared. It just means that that force from the floor or from the scale has gotten bigger. And the result of that force getting bigger is causing me to accelerate up, right? My weight force stayed the same. The floor force got bigger, and then the forces don't balance anymore. If you have a net force, you get an acceleration. That's what Newton's second law says. I'm wondering if you're satisfied or dissatisfied.
I just don't understand why you set it up like that. Like, why do you set it up the way it is?
Oh, for C? So
Yeah, because that's like the same.
This is F net, and this is M times AY. So you're given an AY in part C. This would be the 55 or whatever it was. So the F net part doesn't change. Now the forces do change, right? When I accelerate upward, I feel a bigger pressure from the floor. So the floor is exerting.
Yeah, that makes sense.
But for us, that scale force up on me is the unknown, and that unknown might end up being bigger. You'll find out it does end up being bigger in part C. Or part B, I guess it is. No, nothing's pushing it. I mean, imagine you're in outer space, right? And you take a rock, you throw it in that direction at 3 meters per second, and it just keeps going and going and going and going. Does it need something to keep pushing it to go at that 3 meters per second?
No, there was an initial force on it, wasn't there?
Well, there was when I gave it a push. Something gave this initially a push before the problem started, right? When I say there was an initial speed at 3 meters per second, presumably it was sitting there and someone gave it a push in that direction. At that point, there was a force, but the 3 meters per second, after that person has touched it and is moving along at 3 meters per second, there's no force associated with that 3 meters per second. It's already cruising along at that speed, and would like to cruise along at that speed forever unless some other forces cause it to do otherwise, and that friction force starts pushing opposite and slowing it down. So it would have just kept happily going along. Well, the idea was it's going up at a fairly good clip, I mean, something like 10 meters a second, which sounds pretty fast for an elevator, but I just made the numbers up. Suddenly the cable breaks. It was going up at 10 meters per second. All of a sudden it's in free fall. It's like I've thrown a ball upward. It's in free fall. It still goes up for a while before it reaches its highest point, and then it starts going down. So my question is, if we imagine, the fiction that the cable just instantaneously breaks while it's going up at 10 meters per second, it's still going to go up a little bit more before it starts going down. Okay, I see I forgot to put my answers up here, but just so you can check, I'll write them up here. In just a minute, we'll go through all the parts of problem 2. But maybe this will raise some questions if I put numerical answers up here. $539 newtons, 704 newtons, 3.333333 seconds. $539 newtons. 0 newtons. 5.10 meters. And 2 answers for G.
Choose your Y plus to be down or up?
I chose my plus X, plus X to be up, yeah. All these, I believe, are phrased in such a way that you should be able to answer the same number even if you chose plus X up or down. In other words, I'm not asking for components of things in your coordinate system. I'm saying, how far does it move? Well, that's something that doesn't depend on what coordinate system you choose. What is the force? Okay, that's a magnitude of the force. Or what does the scale read? That's a force magnitude. How many are done with part 2? Just problem 2, I mean. Is it? I think it's especially, even though some of these may seem simple, it's important to get the formal way that we do answer these kinds of problems straight now, because they're going to get more complicated and you need that formalism to hang on to. Okay, let's start talking about the parts of 2 together. It's very similar to the one that we had over there. There's a woman standing on a scale. What does the scale read? Well, you might think superficially that, a scale should read the force that's down on top of it. So maybe the scale would be the subject of my free body diagram. I don't know the mass of the scale, though, so that's going to be a problem when I do F net equals ma. So it seems like a bad idea to use the scale as the subject of the free body diagram, even though it involves the force we're interested in. Rather, I'm going to use the woman as the subject of the free body diagram, because by Newton's second law, the force that the scale exerts on her is going to be equal and opposite to the force that she exerts on the scale, and that's what we're being asked for in many of these parts. So here's the woman. Again, I put her mass in kilograms in the box just so I remember what the box means, because there's more than one object around in this problem. So there's a weight force going down. That's just mg. I'll just label it as 55 times 9.8 just to kind of put some of the numbers in. When I see an mg, I know that's a weight force. And then what we're asked for is how hard she's pushing down on the scale. That's going to be the same as the magnitude of the scale force on her. So I'm just going to write that as a scale, F scale, as how hard the scale is pushing up on her. You could have written it as Fn for a normal force. It is a normal force from the scale, but maybe this is more descriptive. And I don't see any other forces that are in this problem. In order to apply F net equals ma, you know, I could take plus y to be up. You could put plus x in there. Again, there's no forces in the x direction. There's no motion in the x direction, so we're not really going to use F net x equals max. And then the third step, sum of the force y components equals may. So I'm imagining F scale represents that magnitude of the scale force. Its y component is positive because in going from the tail to the tip, I'm moving along plus y. So F scale comes in with a plus sign, whereas the weight has a negative y component. We're talking about y components there, so we've got to put in the correct signs. 55 times 9.8. And in part A, if that's what we're doing here, the elevator is stationary, and that means the woman's y component of her acceleration is 0, and therefore all the components of the acceleration are 0, including the y component. So those two add to 0, and therefore F scale is 55 times 9.8, very close to 550 newtons, 539 newtons. Questions on A? That was really a repeat of the one we just looked at. B. Elevator accelerates up at 3 meters per second squared. Well, here, I'm going to do something. Maybe this is annoying from a student point of view, but I'm just going to alter things in what I've already got written up there to turn A into B. What's different? As you're accelerating upward, well, you still have your weight force. The scale is still pushing up on you. Otherwise, you'd be in free fall. You're clearly not in free fall if you're accelerating upward at 3 meters per second squared. So the scale's got to be pushing up on you, and that's still what I want to find. It is the right-hand side that's no longer 0. If the elevator's accelerating upward at 3 meters per second squared and the person is just rigidly attached to the elevator, they're going to be accelerating up at 3 meters per second squared. M is always the mass of the person or the thing in the free body diagram. And in this case, since the acceleration is upward, the y component of the acceleration is positive 3 in SI units. If I had chosen plus y downward, AY would have been minus 3. But the signs of these would have both flipped too, right? This one would have been plus and this would have been minus. So everything would change sign in the equation. And therefore, in B, the scale force is going to be bigger than it was before. It was 55 times 9.8. Now it's that plus 55 times 3, a bigger number, 704 newtons. You feel in every respect just like you're heavier. That's sort of a, something that seems mysterious in Newton's laws, but if you study Einstein's theory of relativity, he sort of took that literally and said, well, gravity, when you're sitting in a gravitational field, normally at rest, you feel in every respect like someone who's accelerating at a constant rate. And if you take that literally, that those two are exactly the same thing, that was what led him to the general theory of relativity. That's not for us here, though. C. If the elevator accelerates upwards at 3 meters per second squared until it reaches 10 meters per second, starting from rest, how long does it take? That sounds like kinematics. Right? How long does it take to get from 0 to 10? Oh, that sounds like I want in C, V y final equals V y initial plus AY times T. Vy final will be my 10, right? It's going up at 10 later on. Vy initial was 0. Ay is plus 3. Don't put it, the sucker answer is 9.8 or not minus 9.8. Person's not in free fall. They're in an elevator that's causing them to not be in free fall. They're accelerating upwards at 3. So that allows me to solve for t. Just a kinematics practice problem. Questions so far? D, after reaching an upward speed of 10 meters per second, the elevator maintains that velocity. That means 0 acceleration. So the answer for what the scale read is exactly what it was when it was at rest. What matters is that the acceleration is 0. We don't care about the velocity or the speed. After a few seconds of traveling upward at 10 meters per second, the cable breaks, so the elevator car is not connected to anything. What does the scale read after it's broken? That's very similar to this kind of calculation that we did here, so maybe we don't need to repeat that. All of a sudden, if I'm taking plus y's up, if you're in free fall along with the elevator, your acceleration is minus 9 point, your acceleration y component is minus 9.8 because plus y is up. You're in free fall. And that makes these two things cancel out in exactly the same way with the numbers here. So 0 newtons. How far is it from the location where the cable breaks to the point where the elevator is at its highest point? Yes, it's moving up at 10 meters per second. If the cable suddenly is cut, nothing's pulling it anymore. It was already moving up at 10 meters per second. Just like if I throw an object up at 10 meters per second, how high does it go before it comes to rest and then starts coming down again? It will keep traveling up until it slows to 0, and then it will start falling. And that sounds like a kinematics. What number is this? F, letter F. I want to know how far. I know it's initial and final velocity because the final y component of the velocity will be 0. So I'm going to use Vy final squared equals Vy initial squared plus 2ay delta y. We're interested in when it finally comes to rest. What we want to know is how far it travels along y in going from 10 meters per second to coming to rest. It starts with 10 meters per second. Ay is minus 9.8 in my coordinate system, and I want to find delta y. I'm expecting delta y to be positive in my coordinate system, and it is positive. You put this 100 over here, it gets a minus sign, and then I divide out the minus sign, it'll be positive. All right, and the last one, this is just checking. We should have known this back in chapter 2, probably. After the cable is broken, the elevator is at its highest point. The woman inside's in free fall. The elevator's in free fall. The scale's in free fall. Everything's sort of free falling. You know, it's like you toss several items up and they're moving together with each other. They just happen to be nested in this case. The magnitude of the acceleration of the woman is little g, 9.8 in the direction downward. So the magnitude is 9.8. The speed of the woman is 0 at that highest point, momentarily at rest. Okay, questions on that? I think 3, I just found 3 in a collection of some problems, and let's read through it together and see if it's substantially different from those. How much force must you exert with your hand to move a 2-kilogram mass vertically upward with a speed of 3 meters per second? So I'm putting my hand underneath this. How much force does my hand have to exert upward on the bottom of this to keep it moving at a constant, this isn't 3 meters per second, but I couldn't go very long at 3 meters per second, constant velocity of 3 meters per second? Well, the answer is, it's just my hand force has got to balance out the weight because moving at constant velocity, that's 0 acceleration. That means there's no net force on it, and therefore my hand force has to balance out the weight force. So it's just going to be whatever mg is for this. The calculation will look very much like what we did here in this first part, where the right-hand side was 0 in part A. The mass here is 2, not 55, so it looks like my hand force would be 2 times 9.8, 19.6 newtons. How about moving it upward at 7 meters per second? If it's a constant velocity of 7 meters per second, all that matters is AY is 0. So the answer is still 19.6 there. C, what about with an acceleration? That's very similar to what we've done here. So maybe you can fill it in. I will post these on the website, but I don't want to belabor it too much. D, how much force must you exert to move the mass vertically with an acceleration of 7 meters per second squared? Well, of course, it's going to be a bigger force that I have to push up with to overcome that gravitational force by even more to get a larger acceleration. All right, let's do 4 maybe together just because it's phrased in a little bit of a strange way. This might have been related to a homework problem, so when you do get to the homework for chapter 4, maybe that's why I threw this in here as a practice. A block is on a scale in an elevator. We're not told if the elevator is at rest, moving with constant velocity, accelerating. We don't know. We want to find out. When the elevator begins to move, the scale momentarily reads 60% of the block's true weight. Find the magnitude and direction of the block's acceleration at that moment. Well, the scale would have read the block's full weight if it weren't accelerating, right? If it were just sitting there moving at constant speed, constant velocity, it would have read the full weight. So it's clearly got to be accelerating. Does anybody have any intuition about if the scale is reading less than the block's true weight, or if this were a human, that human would actually feel lighter, right? The scale would read less. Which direction is the elevator accelerating in to make you feel lighter? Upward or downward? Downward, yeah. When the elevator, when you're at rest and then it starts accelerating to go up to an upper floor, you momentarily feel kind of heavy. When you get to that upper floor and the elevator slows down, you kind of feel light for a second, just while it's slowing down. And when I'm slowing down in the upward direction, I know it's confusing, you're accelerating in the downward direction, right? That's the direction my velocity is trending. If I had less and less velocity in this direction, that means my velocity is trending towards the opposite direction. It's the same way if you're on a floor and the elevator starts accelerating downward. You for a moment, you feel kind of light, like you don't weigh as much. So the question is, exactly how fast is it accelerating and in which direction? As always, free body diagram. So we've got, in this case, I don't know what the mass of this block is. So I'm just going to kind of hold my breath as we frequently do here. I'm just going to put an M there. Hopefully M doesn't matter because we don't want to know M and we don't know M, but let's just put a mass in. So that means one of my forces on the mass as it's accelerating is its weight, little m times little g. What about if the scale reads 60% of the block's true weight? In terms of the symbol m, how would I label? Well, it's less than that, right? If I really wanted to be accurate, I could say, well, that's going to be smaller. But 60% of it, how could I label it in terms of m? .6 times what? Well, yes, of its true weight, m is a mass, so its true weight is mg, right? So 60% means 0.6 times that value. Okay? And those are the only two forces. Just like in the problems we've been doing, there's only two forces acting on. Because it reads 60% of the block's true weight. And weight is not m. M is a mass. That's different than weight. Weight is mg. So 60% of its true weight would be mg. Here's 60% of its true weight, 0.6 times mg. Okay, and now I'm going to do F net x equals max. Should we choose plus x up or down? I don't really care. Up, okay. Plus x, that's my second step. Third step is always for components, F net, or the sum of the force x components equals max. If we had a y axis, and we'll get into those soon enough, sum of the force y components equals may. And we want to find this AX. And in fact, the sign of AX will tell us which direction it's accelerating, right? If we get a positive AX, it's accelerating up because up is positive for the choice that we made here. If we get a negative AX, it's accelerating downward. So let's find out. Some of the force X components. This one comes in with a plus sign because it's it's going from tail to tip along positive X. 0.6 mg. This one comes in with a minus sign because it's going in the negative X direction from tail to tip. And that's equal to m times AX. And now, why am I relieved at this stage? I can cancel the m that I didn't know. That's good. Otherwise, we might have had an m messed up in our answer, but this tells me what AX is, if you can ignore the slashes there. AX is 0.6 g minus g. If I do 0.6 of something minus 1 of those, I get minus 0.4 of those things. Minus 0.4 times little g is AX. Or I could do minus 0.4 times 9.8, because little g is 9.8 in SI units. That number is 3.92 meters per second squared. Okay, so the magnitude of the acceleration is 3.92. The fact that the acceleration x component is negative means to draw that vector, I better be drawing it from tail to tip in the negative x direction. So it's pointing downward. Jose? I got that because, here I have, if you get rid of all the stuff with the slashes, I have 0.6 g minus 1 g, and I'm simplifying that. Sort of like if we multiply by 10, that would be like 6 of these minus 10 of these, or 0.6 of these minus 1 of those. Well, we're subtracting out something bigger, we're going to get a negative number on what's left over. If you do 0.6 minus 1, you get minus 0.4. Okay, so it's accelerating downward as we intuited, or somebody intuited, at 3.92 meters per second squared. All right, questions on that? All right, that's the whole thing. Let's just take about 2 minutes if you need to go out and use the restroom or something. Let's take a 2-minute break just to kind of get the blood moving a little bit, and we'll continue on with other examples. Okay, let's come back together and talk about the next class of problems, which is the famous inclined plane. If you've ever taken a physics course before, you may think of this as some sort of torture device, but it's actually the next level of complexity where things become a little bit less trivial than just where everything's happening along one dimension. So here is the one we saw in the video. We've got an 8-kilogram box released from rest on a frictionless plane inclined at 25 degrees to the horizontal. So what that means is we draw the horizontal like this. This angle is 25 degrees, and we've got an 8-kilogram box that's released from rest, and it's going to slide down there because there's no friction. What frictionless means, and I talked about this in the video, is that of course this inclined plane is exerting some force on the box, otherwise it would be in free fall and just fall right through the plane. So there's got to be a normal force on it. What frictionless means is that this plane is incapable of exerting a force along this direction on the box. It doesn't try to speed it up or slow it down. The plane I'm just talking about. You know, gravity might try to speed it up, but the plane itself, the surface that it's sliding on, cannot push it backwards or forwards like that. It can push it in the direction perpendicular. That doesn't try to speed it up or slow it down, but you know, friction usually tries to slow things down. So frictionless means that on this box, one of the forces is going to be a normal force, but there's not going to be any friction force that's parallel to the plane. Okay, find the box's magnitude, acceleration, and how far it moves in the next 2 seconds. That last part sounds like a kinematics problem. So we'll forget about that for the moment and just try to get the acceleration first. Hopefully the acceleration is constant, and then we can do a little kinematics problem and be done. Hopefully those are starting to seem easy, especially these one-dimensional ones that we did back in chapter 2. Now, here was a discussion I had in the video. It seems everybody would probably initially have the intuition that let's choose X to be horizontal and Y to be vertical, because, hey, at least the weight force is going straight down. That makes the weight force seem simpler. This is going to make your life really difficult if you choose this, and that's because I know the object is going to slide along this slippery plane. And so if it's going to accelerate when I let it go from rest, it's going to be moving along the plane. That means its acceleration is along the direction of the plane. And notice, in this horizontal vertical coordinate system, this would have both a non-zero x component and a non-zero y component. Going from tail to tip, we have to go both along x and along y. And what that means is, since I'm looking for the accelerations, one of these should be an ay here. I would have two unknowns, ax and ay, which then I would have to take the square root of the sum of the squares to get the magnitude of the acceleration. It's and you could try to solve the problem and see what you run into there. I didn't think it was worthwhile doing it, but you're welcome to try it. In contrast, the better choice is to choose your axes along the direction always of the known acceleration. So if it's moving in one direction, it's got to be accelerating along that direction. So choose your plus x either down the plane or up the plane, and then your y-axis perpendicular to it. Then we know from the very beginning that the y component of the acceleration of this box is 0, and I can use that to my advantage if I need to. Ay is 0. It's not, notice, as it moves along the plane, slides down, its y-coordinate isn't changing. If your y-coordinate isn't changing, ay is 0. Vy is even 0, but your ay is certainly 0. So we're going to choose those. So here's what happened. Free body diagram. Of course, there's a normal force from the plane. If there weren't, this thing would just fall right through. And of course, there's a weight force. Unfortunately, and I know this is a little bit small for those of you in the back, the weight force goes straight down towards Earth. And so the weight force, with the price we're paying for our tilted axes, is the weight force is going to have a non-zero x and y component. But that's okay. To go from the tail to the tip, I would say, well, let's first move along y and then move only along x, and I make a little right triangle. and you've got to figure out how to get that 25 degrees into your right triangle. And we practiced that a little bit before in chapter 3, but this angle right here ends up being the 25 degrees. We can, when we're doing the problem that's on the worksheet, we can work that out in detail if we need to. That's my free body diagram. I've put some axes on it, and so the next step is F net x equals max, F net y equals may. In this case, I already know ay, and so if I can find ax, I'm done. So I'm just going to go for it and just use F net x equals, or sum of the force x components equals max. Again, you'll see I switch back and forth between writing F net and the sigma notation. They mean the same thing. All right, with respect to x components, what's the x component of the normal force? It's 0, right? By definition, we chose the normal is normal to the plane direction, and we chose our y to be in the direction normal or perpendicular to the plane direction. So we're talking about x components here. You don't want to mix up your x's and y's when you're doing F equals ma components. So this one has 0. I could have put a 0 plus there, but there's no reason you need to do that. The weight force does have a non-zero x component. And notice that this weight force, one way to think of it is, yeah, to go from the tail to the tip, I go along the negative y direction, but the plus x direction. Another way to think of it is, look, if your vector is anywhere pointing roughly in the plus x direction, more or less in the plus x direction, that's going to be a positive x component, right? If it's pointing more or less in the negative y direction, anywhere in this direction, but that would be a negative y component. So just quickly, you can get the sign sometimes there. And then to get the component, again, here in this case, it's a positive x component, so I'm putting a plus out in front. The length of this vector is 8 times 9.8, that's m times g, but I've got to get the x component, whose magnitude is the length of this side. And I know it's kind of tiny there. This is 25 degrees there, so to get to this side, I have to go across the angle. So that means I take the hypotenuse length, 8 times 9.8, and multiply by the sine of 25 degrees. And that gives me the x component, positive x component here. Okay, so that's F net x. There were only 2 forces, and one of them had a 0 x component. That's the mass of the thing in the free body diagram times the resulting acceleration. I can just solve. In this case, just cancel the 8's and throw the rest in your calculator. So it seems to make some sense, right? It's not going to accelerate downward at the same free fall rate. It probably, if it's going down a plane, it would be cut down by some amount. So this is a little bit less than half of the free fall rate, 4.14. And then that last question, how far it moves in the next 2 seconds, that sounds like x versus t. We're given t, so you look and we know everything about how far it moves there. Sometimes when I'm using this equation, I will put the x0 subtracted off onto the left-hand side. Notice it wasn't really clear about where x equals 0 was here. If I want to avoid that and I'm only interested in how far it moves, what its displacement is, instead of calculating x final, if I wanted to calculate that, I'd have to say exactly where the origin is. I can just calculate x minus x0, and that's just its displacement times t equals 0, and that's all we really want here. But you'd get the same number either way. Okay, questions on that before we do this problem 5? Problem 5 is just a little bit more complicated. The only addition is that in this case, we release this from rest and it starts accelerating down the plane. In problem 5, if I remember correctly, someone is putting an additional third force on it. They're taking their finger and pushing on the block right here in the direction along the plane and directed up the plane, so that this object is moving at a constant speed that's given to you. Instead of accelerating down, we're going to force it, just move it up at constant speed. I can do that with my finger, roughly. And the question is, in that case, how hard must you push? How big does that force have to be? And then in part B, suppose I push with a different force. It's not just the right force to move it up at 3 meters per second. Instead, I push with 100 Newton force. What is the acceleration, magnitude, and direction in this case? I've changed it from the exact right value. So try working on that using the same kinds of ideas. The first time you do these problems, you really want to just kind of mimic what you're seeing, and then you'll get in the habit of doing this. But it's always free body diagram, then axes, then F net equals ma, components, one component at a time. Yeah, so this force will clearly have a negative x component. Are you okay with that?
Yes.
And the normal force, which is going exactly perpendicular to the plane, will have 0 x component. It will have a positive y component, but 0 x component, right? So the confusing one is the weight force, because it's neither all x nor all y. Let's just look at this picture here. Here's the weight force direction, straight down, right? So we know the magnitude, the length of that vector is 8 times 9.8 mg. And what we want to find is, here's the direction perpendicular to the plane. So I'm going just first along y and then just along x to get from the tail to the tip. What I want to find, if we're talking about x components, is the length of this side. So I need an angle in this right triangle here. And your question, I think, first of all is, well, I know this angle is 25. What is this angle or this angle? Are you okay with that being 25? Yeah. So we know the hypotenuse, and we want this side over here. And when I know the angle up there, when I start at the known hypotenuse length, then I go to this side. Am I going across the known angle or pivoting through the known angle? Yeah, when I go from the hypotenuse to the side I want to know, I'm going across it. And if you can remember, going across is associated with the sine. You just multiply the hypotenuse length times the sine to get the length, the sine of that known angle, to get the length of that other side. Now you see a lot of these sort of pointless vector exercises and trigonometry things, they're coming together finally here. So they weren't so pointless after all. Oh, my answers I got are 245 newtons. That's for A. And in B, I think it's accelerating, and there I get 2.9 meters per second squared in the direction down the plane. How many have had success with A? I just want to see how many people are. Okay, so maybe about half the class. Seems like they're doing okay with A. Most people are still working on B. I'll give you another minute and then we'll do it together. Okay, let's come together on A. The idea is usually I draw my free body diagram separate from any sketch, but I try to, if I have a box or something like that, sometimes I'll just try to make it look like it's in the same orientation. It just helps me draw the free body diagram a little bit. So we got a 50 kilogram object. Of course, it's got its weight force going down, magnitude 50 times 9.8. Of course, it's got the same normal force as before. We'll call that F normal. And in this case, someone's also pushing in this direction, and I believe, if I remember correctly, raising it up the plane. And that force was unknown. We're just going to call it F here. And the question is, how big does F have to be? So here's a force of length F, or magnitude F. I want to figure out how big F should be. Okay, so one more force than we had in the previous part. And that's step one, free body diagram. Step two, axes. We'll take Y to be perpendicular to the plane direction, and X along the plane. Doesn't matter whether you go up the plane or down the plane, but if I remember correctly, the object is being pushed up the plane. I don't know that that really matters for us here, because if you did part A, you know the important thing is what's the acceleration, and constant velocity means zero acceleration. It's being pushed up the plane at 3 meters per second. Okay, so that's step two, attach some axes. Step three is sum of the force components, X or Y, equals M times the same component of A. In this case, everything seems to be happening along X, including the force I'm interested in, so I'm going to just start with X and hope for the best. We'll find we don't need to use Y at all. Some of the force X components. Well, F certainly is pointing along X, is directly along X. So if this represents the magnitude or length of this force, it's going to be a positive F that comes in here. F comes in with a plus sign because in going from tail to tip, I'm definitely moving along plus X. The normal force has 0 X component. If you really wanted to, you could put that in, but of course we don't need to. And this part over here has a negative x component in my coordinate system. What that means is, well, I've got to get from the tail to the tip by traveling only along x or y. And I'm going to draw it by first going along y only, perpendicular to the plane, and then finishing up by going only along x and creating a right triangle. And the idea is this was on a plane that looks like this. This angle is 30 degrees. If I've made a right triangle here, this one's 90 degrees, so these two have to add up to 90 degrees. That means this angle is 60 degrees up there. These two are also, they form a right angle, so these two have to add up to 90 degrees. If this one's 60 here, then this angle here is 30 degrees. And I've made a bit of a mess of my diagram here, but the length of this vector is 50 times 9.8. That's the hypotenuse of the right triangle I've created. I'm interested in the x component of that force, which is this side. So I want the length of the hypotenuse, 50 times 9.8 times the sine of 30, because I'm going across that angle. Or you could use SOHCAHTOA. 50 times 9.8 times the sine of 30 degrees. And I don't remember what I said before, but the sine of this in my coordinate system is negative. So that should come in with a minus sign here. Maybe I was remembering what I chose in the other problem that we were doing. But for this coordinate system, to get from tail to tip, I'm definitely moving along the minus x direction. So this is the size of a side of a right triangle. You know, lengths of sides are always positive, but you've got to decide whether to put it in the plus or minus sign, depending on which way you're going from tail to tip. And now, well, let's see, that's the left-hand side. That's just what's over here. Now we've got to set that equal to max. That's equal to 50 times, what's the x acceleration in this case? It's 0. The only other number I could imagine you putting in is 9.8. Well, it's certainly not in free fall. It's moving at constant velocity. Constant velocity means the acceleration is 0. That means all the acceleration components are 0, including x. So the right-hand side is just 0. And I can solve for f. F is then 50 times 9.8 times the sine of 30. That's this 245 there. That's how hard I have to push in that direction to keep this thing going at a constant velocity of 3 meters per second or 6 meters per second. I have to push that hard even if I'm lowering it down at a constant velocity. It doesn't really matter what the velocity is as long as it's constant. That's the same as the acceleration being 0. This one in front of the 50, it's because I just, you know, while I was writing this down, I chose plus x to go up the plane. I guess because I was pushing, I just said, pushing in that direction. Let's make the direction I'm pushing plus x, so the f will come in that way. Once I've chosen plus x along that direction, in going from the tail to the tip, remember I've always got to say, if as I need to go just along y and then just along x, or just along x and just along y. In going from tail to tip, when moving just along y, am I moving in the plus y direction or minus y direction? For my coordinate system, minus. In going just along x, am I moving in plus x or minus x? Minus. That's where the minus is coming from. Because we're finding the length of a side of a right triangle. That's just going to give you this part. But that won't tell you whether it should come in with a plus sign or a minus sign, because that right triangle doesn't know anything about your coordinate system. Okay, so I have to push that hard to keep it moving at constant velocity, or even have to push that hard to keep it at rest. That's another case of constant velocity, right? Now in B, suddenly we start pushing with only 100 newtons. What's going to happen if suddenly I decrease the force I'm pushing with to only 100 newtons? Well, the acceleration, I don't know what you mean by drop, but the acceleration was 0 before. It was moving at constant velocity. So it is going to start accelerating. Which direction would it start accelerating if I push less? Right, it's going to start accelerating down the plane, which is the negative x direction here. So If I pushed harder than 245, I would actually start speeding it up in the direction up the plane. But if I don't push that hard, it's sort of like it's winning out and I'm slowly, you know, not keeping up with it if I were imagining pushing it with my whole body. Okay, so what changes here in this diagram? Well, what changes is, in the diagram, only one thing. Now I know this force length has magnitude 100 newtons. So my free body diagram, I'm going to sort of reuse it, but now that's not an unknown anymore. The other thing that changes is the right-hand side isn't necessarily 0 anymore. We're expecting a non-zero acceleration, right? So in B, let's rewrite the sum of the force x components equals max. Same thing happens kind of on the left-hand side, except now I know what this F is. It's 100. Minus 50 times 9.8 times the sine of 30 degrees is equal to the mass of the thing in the free body diagram, that's 50 here, times the resulting acceleration x component. And that's what I endeavor to find here. So then I solve for ax. It's the only unknown there. And you get, in this case, I would get a negative ax. Ax is minus 2.9 meters per second squared if you calculate it. If you chose plus x down the plane, you would have gotten positive. The question is, what is the magnitude of the acceleration and the direction? Well, so this is telling me the magnitude is 2.9, and the minus sign is telling me it's accelerating in the negative x direction. So that's down the plane. Good. Any more questions about these kinds of problems? Thank you. Oh, yes. It doesn't. I mean, tell me if this is what you're thinking. I might have said, oh, I prefer to go first along x and then along y. And that would have been fine. You know, I'm still looking for the length of this side. I want the x component of this form. And then in that case, I would have been happy that I knew that 60 degrees over there. And I could have said 50 times 9.8 is the length of this times the cosine of 60. But the cosine of 60 is the same thing as the sine of 30. So we'd get the same number in that case. We'd have to put it, for my coordinate system, we'd still have to put in the minus sign. Anything else? All right, we're just, I will say the order I'm doing things you'll find is a little bit mixed up compared to the way Giancarlo does it. We're gonna all come together by the reading that you're doing tonight, and we're just gonna continue going through stuff. So some of the stuff doesn't occur till some of the sections you're gonna read tonight, including this inclined plane stuff, but this is the way I prefer to introduce it, and we'll all get to the same place. So I think this is a good place to stop. We'll start talking about the strings and pulleys, which I know you saw in the video. We'll do problems associated with those tomorrow. Bring this worksheet back. There's still several more problems that we'll be working on tomorrow. And at least one person asked about office hours. As always, I'm having office hours after class ends right here. So hang out if you want to talk about homework or anything else.